Hello everyone, this is Alice Gao. In this video, I'm going to talk about how we can design an admissible heuristic function for the A-star algorithm. In the previous video, I introduced the A-star algorithm. The A-star algorithm has a nice property. If the heuristic function is admissible, then A-star is guaranteed to find an optimal solution. This leads to an important question. How do we come up with an admissible heuristic function? Let me use the A puzzle as an example. There are a few well-known heuristics for this puzzle. I have two of them on the slide. The first one is called the Manhattan distance heuristic. On a grid, the Manhattan distance between 2 points is the sum of their horizontal distance and their vertical distance. For example, in the initial state on the left, the Manhattan distance between 5 and 4 is 3 because their vertical distance is 2 and their horizontal distance is 1. How do we calculate the Manhattan distance heuristic? Given a particular state, we need to consider every non-empty tile. We will calculate the Manhattan distance between the current position of the tile and the goal position of the tile. Add this value for all the non-empty tiles together, and we get the heuristic value. Let's calculate the Manhattan distance heuristic value for the initial state on the left on the slide. Please pause the video and calculate this value yourself, then keep watching for the answer. Let's calculate the heuristic value together. I have labeled each tile with its goal position so that we can visualize the distance between the current position and the goal position. For tile 1, the distance is 1, 2, 3, and 4. For tile 2, the distance is 1, 2, and 3. Let's keep going. For tile 3, the distance is 1. For tile 4, the distance is 2. For tile 5, the distance is 2. For tile 6, the distance is 0 because it's already in its goal state. For tile 7, the distance is 2. And for tile 8, the distance is 2. Calculate the sum. The sum is 16. So the Manhattan distance heuristic value for this state is 16. The second heuristic is called the misplaced tile heuristic. For every non-empty tile, if the tile is not in its goal position, then we'll add 1 to the heuristic value. In other words, we will count the number of non-empty tiles that are not in their goal positions. Let's calculate the misplaced tile heuristic value for the initial state. Please pause the video and calculate this value yourself. Then keep watching for the answer. Let's calculate the heuristic value together. I've already written down the goal positions of the non-empty tiles. How many tiles are not in their goal positions? Well, out of the 8 numbers, 6 is the only one that's in its goal position. So 7 out of the 8 tiles are not in their goal positions, which means that the heuristic value is 7. Both the Manhattan distance heuristic and the misplaced tile heuristic are admissible. I will explain why very soon. How can we construct an admissible heuristic function? Let me describe a general procedure you can follow. First, take the original problem and relax it. How can we relax a problem? Usually, the problem has some requirements. These requirements are expressed as constraints. Take these constraints, simplify them, or remove some of the constraints. Once we relax the problem, we will solve the relaxed problem optimally. The cost of the optimal solution to the relaxed problem is an admissible heuristic function for the original problem. Since we're constructing a heuristic function, it's important that the relaxed problem is easy to solve. In other words, solving the relaxed problem should not require search. A problem is quite challenging if it requires search. The heuristic function should help us solve the original problem. If it's challenging to construct the heuristic function, it defeats the purpose of having the heuristic function in the first place. Let's apply the general procedure on the 8 puzzle to derive some admissible heuristic functions. First of all, how can we relax the 8 puzzle? To relax the problem, we first need to define the constraints formally. What are the rules when we move a tile from its current position A to another position B? There are 2 requirements. First, A and B must be adjacent. We can only move to an adjacent position. Second, the target position B must be empty. Let's relax one or both of these constraints. What does a relaxed problem look like? What heuristic functions can we derive from these relaxed problems? Let's relax the 8 puzzle in 2 different ways and derive 2 admissible heuristic functions. Question number 1. Let's remove the second constraint, B must be empty. In other words, we can move a tile to an adjacent position, but the adjacent position doesn't have to be empty. If we solve this relaxed problem optimally, which heuristic function will we get? Remember that the cost of the optimal solution to the relaxed problem is an admissible heuristic function. Pause this video and solve this yourself. Then keep watching for the answer. The correct answer is A. We get the Manhattan distance heuristic. Please watch a separate video for a detailed explanation of the answer. Question number 2. What if we remove both constraints? In this relaxed problem, A and B don't have to be adjacent and B doesn't have to be empty. In other words, we can move a tile from one square to any other square in one step. If we solve this relaxed problem optimally, which heuristic function are we going to get? Pause the video and solve this yourself, then keep watching for the answer. The correct answer is B, the misplaced tile heuristic. Please watch a separate video for a detailed explanation of the answer. Having worked through the 2 questions, you might be wondering about the third possibility. If we remove the first constraint and keep the second constraint, we can derive yet another admissible heuristic. This third admissible heuristic is called the Gashnick's heuristic. This heuristic has some very interesting properties. I encourage you to explore its properties on your own. Given a search problem, we can often relax it in multiple ways and derive several different admissible heuristic functions for the same problem. With multiple heuristic functions, which one should we choose? Let me discuss a few ways of comparing heuristic functions. First, we must require that the heuristic is admissible. This allows A star to find the optimal solution. Next, a nice property is that the heuristic function produces different values for different states. This type of heuristic can help us distinguish different states and decide which state to expand next. On the other hand, if the heuristic function is constant, that is, it has the same value for all the states, then that's not a very useful heuristic function. Finally, we want the heuristic values to be as close to the true costs as possible. The closer the heuristic values are to the true costs, the more accurate the heuristic functions are. This picture illustrates the first and the last points. H star is the true cost, and H is a heuristic function. The heuristic function should be admissible, so the heuristic value should be between 0 and the true cost value. Then suppose that we have two heuristic functions. H1 and H2 are both admissible. In this case, we prefer H2, which is more accurate since it's closer to the true cost. On the previous slide, I discussed a few intuitive rules we can use to compare heuristic functions. Next, let's look at comparing two heuristic functions formally using the concept of dominating heuristic. Given two heuristic functions, h1 and h2, we can say that h2 dominates h1 if two conditions are satisfied. Condition number 1. For every state, h2 produces a weakly higher value than h1. Weakly means greater than or equal to, so the two values can be the same. Condition number 2. There exists at least one state where h2 produces a strictly larger value than h1. In other words, for every state, h2 is weakly higher than h1, and for at least one state, h2 is strictly higher than h1. One consequence of this relationship is the following theorem. If h2 dominates h1, the running A star with h2 will not expand more nodes than running A star with h1. Therefore, if we use h2, A star will spend less time exploring the search graph and find the optimal solution faster. Let's apply the idea of dominating heuristic to the two heuristics we derived for the 8 puzzle. The two heuristic functions are the Manhattan distance heuristic and the misplaced tile heuristic. Based on dominating heuristic, which one is better? Does one heuristic dominate the other, or neither dominates the other one? Pause the video and solve this yourself. Then keep watching for the answer. The correct answer is A. The Manhattan distance heuristic dominates the misplaced tile heuristic. Here's the intuition. Given a particular state, consider each tile that's not in its goal position. The misplaced tile heuristic will add 1 to the heuristic value for each tile, for each such tile. The Manhattan distance heuristic will add at least 1 and possibly more for each such tile. Therefore, the Manhattan distance heuristic always produces a weakly higher value than the misplaced tile heuristic. Please watch a separate video for a detailed explanation. That's everything I want to discuss on designing an admissible heuristic function. Let me summarize. After watching this video, you should be able to do the following. Describe the procedure of designing an admissible heuristic function by relaxing a problem and solving the relaxed problem optimally. Design an admissible heuristic function for a problem by applying the procedure. Compare two different heuristic functions. Provide reasons for why we should prefer one heuristic function over the other one. Thank you very much for watching. I will see you in the next video. Bye for now.